Static equilibrium 4. We've got another beam problem here, but this time the weight of the beam is not negligible. We've assumed up to this point that the beams don't really have any appreciable weight, but this one does. We are assuming that the beam is uniformly distributed. We need to consider all of its weight to act as an additional point load at the beam's center of mass. So the beam's center of mass is right here. And we need to consider, for the sake of finding the reactions, we need to pretend that all of this weight is acting right here at the center of mass. The weight of this would be m times g, so that would be 500. I'm going to draw in a 500 Newton force right there. I'm drawing it as a longer arrow just so that I can fit it in here. Right there, 500 Newtons. That's where that came from, boom, right there. And that needs to act at the center of mass of this beam. How long is the beam? 16 meters. So this is going to be 8 meters from each end here. And once we've done that, then we just proceed normally and we're good to go. You ready? The ups equal the downs. Let's put reaction A pointing up, reaction B pointing up. We assume they point up. Maybe they don't, but we'll assume that they do. If they don't point up, they'll just come out to be negative numbers. The ups equal the downs. RA points up, RB points up, we think, and the other stuff points down. That's going to be 500 down, 700 down, that's 1200, plus another 550, 1750. So that's one equation. One more time, we can't just cut 1750 in half and assign it to RA and RB both. Unless the system is perfectly symmetric, then you can do that, but otherwise you can't. And when you can't, then you have to write a torque equation, or in civil engineering you call it summing the moments, which is the same thing. But we have to pretend we have an imaginary pin somewhere, and usually we want to put it over one of the unknowns so that that doesn't appear whenever we do our torques. So let's figure out what all of these other forces do with regard to torque. Let's do RB first. RB, what's the lever arm going to be? 16. Everything is measured relative to the imaginary pin. How about this 550 Newton force? How far away is that? 4 meters. And then we have a 500 Newton force, which is 8 meters from our imaginary pin. And then we have a 700 Newton force, which is 14 meters away. And it looks to me like the RB torque would be a counterclockwise torque. Again, we are assuming that this pin here on the left side is fixed. And then each of these other forces would cause this thing to rotate clockwise, 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 which says to me that all the clockwise torques should be on one side of the equation and the counterclockwise torque on the other side of the equation. We can solve this equation. I won't insult your intelligence by typing that in for you. I think you can add all that stuff up on the right side, divide through by 16, and when you do that, you get RB to be 1000 newtons. And because it came out positive, that means it does in fact point upward like we thought it did. And if RB is 1000, we put that back into our force equation, and RA comes out to be 750 newtons. Also positive. In other words, it also came out to be pointing up, just like we thought. Whenever you have a beam that has a non-negligible weight, you want to take the weight of that beam, put all of that weight right in the middle of the beam, and then we just solve the problem using point loads